name is Igor Sviligoy from the San Diego Supercomputing Center. Just to acknowledge that this work was done together with Emily and Jeff from General Atomics and Ruben from ORNL. I'll not read you back the title. Let's go straight into the talk. So what we are talking about? Well, we are talking about Fusion codes. And for anybody who knows Fusion, you will know it's very compute and memory intensive. And in particular, we are talking CGYRO, which is a widely used first principles based simulation tool. It has a long history. It has always been in Fortran, but it was originally CPU only, but was eventually ported to NVIDIA GPUs at the time when Titan came alive, and we used OpenACC for that. Now, recently, Frontier at ORNL came along with AMD GPUs, and we had to find a way to use them. Now, I hope everybody knows OpenACC, and you know what it looks like. Here you see, you just add a few pragmas. There is nothing NVIDIA specific here, so how hard could it be to just run it on an AMD GPU? Now, there is a problem with OpenACC and not NVIDIA environments. The OpenACC was developed as a GPU-specific alternative to OpenMP, and it was the only derivative-based option at the time. It was spearheaded by NVIDIA because it was the only play in town. It was embraced by CRAY. Unfortunately, since then, AMD and Intel came along with their own GPUs, and they said, nope, OpenACC, we don't want even look at it. Now, since then, OpenMP has added GPU support, which is similar, but it's not identical. So we didn't want to go there directly. So how do we go ahead? Now, Frontier, which was our target and is AMD GPU based, it's a HP CRAY machine. And as I said, CRAY supports OpenACC, which is great. Although it supports it only for Fortran, but luckily for us, our code is in Fortran. So voila. We're supposed to just recompile it. Now, we never used the CRAY compilers for our GPU code before because NVIDIA does such a good thing with their compilers. We never feel the need. So as you can imagine, the first time you try a new compiler, some things just don't work. They were all minus things. Looks like CRAY is a little more strict about interpreting some OpenACC standard rules. It was mostly about scalars. All small things, took a few tries, but we went over it. The one thing that really tripped me was that the CRAY compiler has a sync by default semantics for OpenACC, while NVIDIA has it synchronous by default. You can make the compiler be synchronous by default with an compiler option, but it's not out of the box. So that took a couple of days of scratching my head and trying to figure out why things weren't working. Not a big deal once you know it, but definitely was not expected. Another thing is external libraries. Most codes I know of are not completely in-house. They have some external dependencies. Luckily for us, CGYRO has only one large external dependency, which is FFT compute. And we have been always using the FFTW interface, as is for CPUs, and using the FFTW-like batch QFFT interface on NVIDIA GPUs. We couldn't use it as is on the AMD GPUs, but AMD has something almost the same as part of HIP FFT. It's very similar to the QFFT FFTW interface. You just replace Q with HIP, and there are some small minor details that are different, like you see here. But yeah, apart from doing a nice if-def, it was pretty much painless once we figured out how to actually invoke it. So all good so far. So we were able to compile it in a matter of days. And at that point, we said, OK, woohoo, we have the code. Let's run it. And of course, it was going pathetically slow, at least for what the AMD GPUs were theoretically spec'd as. So how do we go on? Well, looking closer, we have essentially some timers in the different parts of the code, and we notice that one section of the code was actually very fast, as fast as we were expecting the AMD GPU to be. So what was so different about this part of the code and not the others? Looking closer, it turned out that it was an only place where we put explicitly gang vector in the ACC parallel loop construct. It's supposed to be completely irrelevant. The compiler should do the right thing, so we mostly didn't bother, apart from that part for whatever reason that day I was feeling pedantic and put it in. And I said, could that actually be? So I added gang vector to all the other places where we have parallel loop, and well, two of the sections, the field and the stream section, I'm not going to details what they mean, they're just pieces of code. You see, we got a huge drop in runtime by just adding those. So it looks like the CRAY compiler really likes if you are pedantic and add that, while NVIDIA basically doesn't care. So that was an eye-opener, and it sort of mirrors my expectation that using different compilers will give you different optimizations. So relying too much on the compiler optimization is usually a bad idea. Unfortunately, you see, yes, it worked for two, but the other, I still had a couple that didn't, and this got way better, but not enough. It was still significantly slower than on NVIDIA. So what should we do? Looking around, there was really nothing obvious that should be going wrong. So I said, okay, let's see what the algorithms do. Maybe they're doing something stupid. And turns out we actually did something stupid. In the first part, in the shear, we were trying to be smart, and we created a temporary table inside the loop, pre-compute some values, and then reuse them many times. Turns out that that actually slowed down the whole code. It's better to do more compute than mess up with memory, which is true in most cases, but it was particularly true in this case. Surprisingly, it was a total performance killer for AMD, and only marginally slower on the NVIDIA GPUs with the NVIDIA compiler, so we never noticed before. For the other code, I was able to simply refactor the code and get rid of reductions. So again, a little less ideal traversal of the memory, but getting rid of reductions. And in both NVIDIA and AMD GPU case, it was a win, to my surprise. But it affected the code on Frontier way more than it did on the NVIDIA GPU. By the way, we are using Perlmutter as a GPU benchmark there. We didn't look in detail if it was due to compiler or hardware issues. We solved the problem and we're happy. Now, there was still one piece, and that was FFT, and that is an external library. So I was stuck on that for a while because I said, that's an external library. Why is computing FFT on AMD GPU so much slower? All the things that AMD published claim that FFT should fly on their GPUs. Well, turns out we were doing something stupid again. For those who know FFT, you know that when you do two-dimensional FFT, you often do zero padding to avoid aliasing. And that padding is somewhat flexible. And we were just doing it in a stupid way. So we got very large primes when you decompose the size. By essentially adding a +1, we got back to small primes. And of course, we got a significant speed up. Again, the NVIDIA FFT was marginally faster, but the difference in time spent on the AMD GPUs was just huge, which seems to imply that the NVIDIA libraries are way more optimized for edge cases that the AMD GPUs are. You should never do it the wrong way, but it's good to know that NVIDIA has put effort into non-ideal cases too. So that was pretty much all we had to do. Now the AMD GPUs were actually faster than the A100s, which is what we expected. So we said we're happy. But you see, we significantly improved our code on the NVIDIA GPUs in the process too. And just to show it was not for the small benchmark case, we got a really big case, which uses 288 GPUs. And you see the AMD GPUs are even faster relative to the NVIDIA GPUs there, which is great. So lessons learned. If you have a Fortran OpenACC code, it's perfectly doable to port it to the AMD GPUs based HPC system, at least if you have access to the CRAY compilers. I tried to compile with AMD provided FLang, and it didn't even compile. I would not recommend even trying there. We did find a few minor issues with the CRAY compiler, but nothing too bad. It was just a couple of days of head scratching for the dialects. And in general, the fact that we now have two completely different hardware platforms with different compilers actually helped us to spot suboptimal code that we didn't know we had. Now, it's definitely not the only way you should try to optimize your code, but this was definitely a good guide and motivator to go and actually fix those parts of the code. And that's pretty much all I have. I just summarize what I've done here. And I would say, yeah, the experience was not too terrible. Took maybe a FTE week from start to end. And we are pretty happy on how CGYRO works on the Frontier AMD GPU-based system now.